All right, good afternoon. I'm Chris Lorenz. This is Jeffrey Prakash, John Fuller, Kwon-Sing Lee, and Anthony Park. And we're the team from the University of Illinois in Urbana-Champaign. And our concept for this year's Inspiration Mars International Design Competition is Project IMMORTAL. IMMORTAL, which stands for Illini Mars Mission for the Opportunity to Revitalize the American Legacy, which is an innovative mission architecture which utilizes existing technologies in as many places as possible to allow for this near-term mission to be accomplished. The requirements that we identified when we first started looking at this are the launch in 2018, January 2018, for the window that we have, using 2 crew members, keeping it at the lowest cost possible, using only American components as per the original Inspiration Mars design, and using only existing or well-developed technologies with a technology readiness level of at least 6. And then the driving factors that we identified as we started moving through this process are the re-entry capsule that will bring the astronauts back home, the propulsion systems that will carry them out to Mars, as well as the deep space habitat and the associated life support systems. Especially in the case of the re-entry capsule and for the deep space habitat, these are going to be carried throughout the mission, so any small increase in mass that might occur there is going to lead to a large increase in total system mass, so we wanted to make sure to minimize these. The concept that we ended up coming up with is shown here in this diagram. As you can see, our first launch is of a Falcon Heavy, which will launch the Dragon capsule along with a modified Cygnus module, similar to the original Inspiration Mars plan. Followed shortly by a second launch, which is a Delta IV Heavy, carrying an additional 4-meter Delta cryogenic second stage. These 2 will dock in low Earth orbit and perform the trans-Mars injection burn, first from the excess propellant on the Falcon Heavy upper stage. Following this, there will be one orbit with a period of about 4 hours, and a second burn from the Delta cryogenic second stage. After these burns are complete, the Dragon capsule will uncouple from the spacecraft, turn around and dock back to the spacecraft in the same style as the Apollo missions. The astronauts will then go on their way to Mars, fly by at an altitude of about 100 miles, and return to Earth in 501 days. The mass, the total system mass that we came up with for our architecture is a little bit less than 16,000 kilograms for the dry mass alone. This is not including propellant, of course, also not including the dry mass of the systems. The largest masses here come from the life support systems and the structures, such as the re-entry capsule and habitat themselves. The launch vehicles that we identified, like I said, are the Falcon Heavy, which can launch approximately 53,000 kilograms to low Earth orbit. Since we're only launching about 16,000 kilograms, we've calculated that we'll have 30,300 kilograms of propellant left over in low Earth orbit, which we'll use as a part of the trans-Mars injection burn. In addition, we'll be launching a Delta IV Heavy to launch a 4-meter Delta cryogenic second stage as a propulsive stage. This stage has a total mass of about 24,000 kilograms, so it'll fit nicely within the roughly 28,000 kilogram capability of the Delta IV Heavy. Here you can see the payloads inside of their fairings. There's the Dragon capsule with the Cygnus and service module located below it, as well as the Delta cryogenic second stage with an aerodynamic fairing added on top to allow for launch.
Here you can see the propellant budget for the mission, majority of which is used during the Falcon Heavy burn and the Delta cryogenic upper stage burn. But while we have accounted for the boil-off that will occur during the loiter as well as the rendezvous phases of the mission, although they are less significant compared to the total propellant uses. And the burn will occur on January 2nd, 2018, within about a week period either way, allowing for launch delays. And will result in a 501-day trajectory, 227 days outbound to Mars. The flyby will occur, and then 274 more days as they travel back to Earth. And you can see the C3 for the trajectory is shown, and they will have the ultimate entry velocity of 14 kilometers per second as they return to Earth. Here you can see an STK simulation of the flyby, and you can see they travel towards Mars and they'll perform the flyby. And now, then the longer stage of their mission, they will return to Earth, taking a relatively low perihelion, almost to Venus level orbit, although not quite near Venus. And then they will finally return to Earth. And the habitat design was one of the more important elements of the design, as just the re-entry capsule would not provide sufficient room for the astronauts to have a comfortable stay over the course of the 500-day mission. We considered Bigelow modules, although we determined that they would be not quite ready in time, and they would likely be too large for what we would be able to accommodate on the launch vehicles. So we decided to go with a variation of the Cygnus cargo module that has so far flown on the International Space Station. The standard enhanced Cygnus were not quite large enough for what we thought would be necessary, and so we proposed to further extend the Cygnus into a super enhanced variation while keeping the same diameter to allow for ease of manufacture, and it would increase the volume while not significantly increasing the mass of the module. In addition, we would add a custom service module to allow for the life support over the 500-day mission, along with the increased power requirements, allowing it to be serviced from the inside of the spacecraft. And the other important part of the mission was finding the re-entry capsule. And we considered the Orion capsule, but it was determined that it would not be ready in time for the 2018 timeframe of the mission, at least in a manned capacity. And so we decided to look instead at commercial vehicles, and we decided that the Dragon would be a better option than the CST-100, as it, while both would be ready in 2016 or 2017, the Dragon is more applicable to the deep space environment due to its Pika-X ablative heat shield, which is based on the legacy Pika heat shield used on the Stardust mission, which came in at an entry velocity of 12.9 kilometers per second. Although significant testing will still be needed for any heat shield because of the immense re-entry velocity that the mission will entail. And they will have to deal with testing the materials, as the current facilities are not quite sufficient for the full 14 kilometers per second. And once the Dragon completes its re-entry, it will either do what, as SpaceX has proposed, is powered landing, or in the event that that is not a viable option, it can simply use a parachute landing like a more conventional capsule.
So the solar intensity at Mars is roughly 50% of what it is at Earth. So we decided that we're going to take the Cygnus solar panels that they have on and expand the ZTJ gallium arsenide cells to 40 square meters. This will allow us to have the required 10 kilowatts that will be used to power our habitat at Mars. Now, while we're closer, we can use the extra power that we're going to generate to charge nickel and hydrogen batteries, which will be used when an eclipse happens during the flyby of Mars, or if we have any damage to our solar cells, we can continue the mission by using our batteries. As you can see, our life support is 40% of our power budget, caused by this command control, data handler, and thermal. So these batteries are going to become very, very useful if any of these need extra power for any reason at all. Our communication antennas are going to communicate with Earth through the DSN. We're going to have a high gain antenna using the UHF radio that has been proven on Curiosity. We're also going to use, it's going to be our primary communication antenna, and we're also going to use a low gain antenna, which is slower, to do non-critical uploads that will allow us to keep the high gain antenna free for service. Our attitude, control, and navigation, we have a very robust system using inertial metric units and measurement units and solid-state star trackers, as well as a sun sensor, which will allow us to know exactly where we are. And we will have a very, since we have one major burn transit, if we need to make any corrections for anything that might have gone away, we have a precise 3-axis control using Aerojet MR-170Vs, 107V thrusters, which are hydrogen propellant with 220 newtons of thrust, and 2 sets of momentum disks. And in our mission architecture, we've also made an allowance for 7 correction maneuvers, which will allow us to correct anything that may have gone wrong.
For the environmental control and life support systems, there are many components. These, we have, one of the more important components are the water recovery system, air revitalization system, and waste hygiene system. These systems are based heavily on the current systems that are used on ISS modules at this point in time. We have also implemented an active thermal control system for safety of the astronauts to allow the habitat to dissipate excess heat. This system consists of 2 Friedel 21 coolant loops, liquid-liquid heat exchangers, and 4 heat sinks. This system is able to dissipate up to 20 kilowatts of heat dissipation and it allows the habitat to withstand the harshest thermal conditions that it faces. All these systems have to be internally serviceable due to the structure of the habitat. We have also noticed that the astronauts on board will suffer mentally and physically during the duration of the trip. In terms of mental health, the astronauts may have psychological effects due to the long-term isolation We also noticed that astronauts do tend to suffer from sleep deprivation or lack of quality sleep. Therefore, to counter these mental health issues, we have decided to use either medicine or technology, such as lights that are able to simulate day and night cycles, to allow the astronauts to have sufficient quality sleep. In terms of physical health, the astronauts do face loss of bone mass and loss of muscle volume due to the long duration spent in microgravity. In order to minimize such issues, we have decided to use dietary measures, pharmaceuticals, and equipment such as the advanced resistive exercise device that will allow the astronauts to participate in exercises while on the mission.
So solar particles deflect galactic cosmic radiation, and since we're launching during a solar minimum, our main concern is the GCR because it'll have a higher flux. With galactic cosmic radiation, we have to worry about is the high energy heavy ions that have the potential to produce secondary radiation when they interact with their shielding material. So for our passive shielding, we want to focus on having higher shielding performance compared with aluminum, while without increasing mass significantly. And what we ended up choosing was polyethylene, and you can clearly see why on the figure on the right. What we looked at were high TRL shielding materials, and on the y-axis you have equivalent dose at a 5 centimeter depth. So at lower doses, that means higher shielding performance. And on the x-axis, you have aerial density. And as you can see, at almost every given aerial density, polyethylene does the best. So we went with that material. And what's really good about polyethylene is that it preferentially fragments into helium rather than secondary neutrons when those higher energy particles interact with it. The specific type of polyethylene we'd like to use is RFX1 because its material properties it being lighter and stronger than aluminum. We'd also like to use our water reserves and places strategically to add additional protection during this mission. So for dosimetry, we'd like to use a lot of things already being used on the ISS, specifically radiation area monitors, located strategically both inside and outside the deep space habitat. These tools will help identify avoidance areas within the DSH, and we also like to use personal dosimeters. One of the limitations of these devices is that they have poor neutron sensitivity, and we expect more than 10 to 30% of the dose coming from neutrons. So we'd like to incorporate biodosimetry for our mission, specifically the FISH technique, which is short for fluorescence and sensor hybridization. Basically, we're going to paint individual chromosomes of the lymphocytes within the crew member's blood. And after the mission, we can count the specific number of aberrations on those chromosomes, and they'll directly correlate with the actual biological damage they receive in this mission. For the scientific return, we want to focus on low-mass biological sciences, specifically monitoring the crew health and zero gravity, monitoring the radiation environment, and also psychological diagnostics. And also during the flyby, we'd like to take a low-resolution imaging of the Martian surface.
And now we're going to close out by looking at the cost, risk, and timeline analysis that we've done. So for the cost of this mission, as you can see, the largest components that we found are for the launch vehicles, the modified Cygnus spacecraft, and the ground operations that are involved with this. In addition, the modifications that will need to be made to, say, the launch vehicle upper stage, the Dragon capsules, looking at the performance of the heat shield, the new facilities that might need to be created, as well as the modifications to the Cygnus spacecraft have been taken into account for these. We've included a 30% margin on top of all these costs for the case spanning overruns, and our total cost comes out to a little bit less than $2 billion. And as you can see here, we believe this fits nicely into this time frame without excessively high costs in any specific year. The largest cost that we do find is in the last few years here, where we have large ground operations costs, and that's also when we have large costs from, say, purchasing the launch vehicle. And since this is such since any Mars mission really is such a high-risk mission, we took a strong look at risk management. We identified as many risks as we could that might come into play for this mission, and we've ranked them on a scale of 1 to 5 for their likelihood of occurrence and the severity of them occurring. So for example, you can see in that orange box there's a 2, and that means we've identified 2 risks that fall into that category of fairly likely and incredibly severe. And those 2 specifically are the big ones that we're concerned about. Those 2 are the heat shield and its ability to withstand re-entry at Earth, and the capability of our propulsion system using 2 separate burns and the boil off and associated launch windows. Those are the biggest risks we've identified, and we hope to mitigate them by catching them early. And here's the operations timeline that we've identified. We quickly dive into developing the last 2 technologies that are required. While we are at high TRL for most of them, some of them still do require some changes, and there's also some integration that will need to occur. And then within the next year, we dive already into the construction, since many of these are off-the-shelf components. So the IMMORTAL architecture is a pioneering mission architecture to send men to Mars, and it's the nearest term mission that's really possible. And we believe that our architecture is the most feasible one for this 2018 launch window, because it uses these existing technologies to provide such a low cost. And finally, we'd like to acknowledge our Professor Stephen Durso for his guidance and assistance, as well as the assistance of the Aerospace Department at the University of Illinois for allowing us to come down here. And we'd like to thank all of you for being here. Let me take any questions.
Why did you choose using a Delta IV Heavy as well as a Falcon Heavy instead of 2 Falcon Heavies?
Right.
Since the Falcon has more capability and cost less.
Right. One of the reasons we went with the Delta IV Heavy and Falcon Heavy is because Falcon Heavy, the launch manifests for Falcon rockets in general have been pretty crowded, especially with the Falcon 9. And the Falcon Heavy itself has yet to launch and will not launch probably until 2015, I believe, at this point. So we think that given the launch manifest, it might become difficult for us to get 2 launches by January of 2018. So we decided to go with the Falcon Heavy and the Delta IV Heavy. Also, integration with the cryogenic hydrogen stage we felt would be easier, since the Delta IV Heavy uses hydrogen stages and the Falcon Heavy uses RP1. That was another big reason. Yep.
You have the Dragon from SpaceX and the Cygnus from Orbital stacked in the Falcon 9 Heavy. Do you anticipate integration problems between the 2?
Yeah, and that's definitely something that we considered. There will definitely have to be some integration work done there. We included that, I believe, in our cost estimates, because that's definitely incompatible components because of 2 different companies.
Right. And a completely different question. You mentioned, as several groups have, the Mars surface imaging. What's your resolution expected?
We didn't identify a specific system for that.
It's something you're going to do.
Right. That's a very minor concern of ours. We didn't want to include anything that would supersede MRO. This was just simply for the purposes of the inspiration side of the inspiration Mars. We need some sort of imaging.
Sure, Mike Malin will sell you something.
Is the shallow back shell angle of the Dragon a concern? No, why not?
That might be a concern. That's something that we'd have to look into. We honestly did look into the back shell angle.
Did you, when I read your report, it seemed to me you were going to transfer the crew to the HAD module after TMI. Did I read that right?
Yes.
So why did you decide to do that later, given the risk? If they can't, they're going to be in dragging for
That-
500 days.
Right, that was due to the geometry of the docking port, because we're using the docking port on top of the Dragon capsule to attach to the Delta cryogenic second stage.
Ah.
So in order to use two different propulsion stages, that was what was required of us.
Okay, okay.
Correct me if I'm wrong, I thought I heard that you said you were going to use ISS type equipment for your ecosystems, all right?
Yes, that's correct.
So, so that's not 100% closed. Did you take that into account, the extra material that you're going to have?
Yeah, you mean it's not 100% recyclable?
Right.
Yeah, yes, we definitely did. We did actually have decent access of water supplies, especially. That's included in part of our radiation shield. I think we have 12 kilograms of water.
Question? Okay. Thank you.